Hi ho. Last video we had a look at a couple of examples of sketching cubics from factor form. This is a couple more examples, just with a bit of a slight difference to them. This one here is already in factor form. In fact, the next two examples are already in factor form. Let's go through the steps again, remembering, seeing if we can remember what it means when we have what we call a repeated factor. Okay, it's still a cubic though, right? Because if I expanded this, I'd have an x squared. And then if I then multiplied the expansion by this binomial, I'd get an x cubed. So I hope that makes sense. That's definitely still a cubic. So it should be one of those shapes. So we'll just start with the right pencil, huh? We'll start with the usual. Start with the y-intercept or the x-intercept. Doesn't really matter, but I usually start with the y-intercept, to be honest. I didn't do it last video, though. So let x equal 0. What do we have then? Y is equal to, and we can just do this bit in our head, right? So this becomes 0, so this becomes 1 squared, which is 1. But then we've got a negative outside it. So 1 squared is 1 is done first, but then it's made negative. So we've got negative 1 here, and we've got a negative 2 here. So we've got negative 1 times negative 2, which is 2. And as usual, I'll put it over off to the side there so it's nice and neat. X-intercept, same dealio. Let y equal to 0 and solve. And so we've got x is equal to negative 1. That's from the first repeated factor. And x is equal to 2. That's from the third factor. The second unique factor, but the third factor. And then the last thing is the dominant term. So I'm just going to go dt. And I'm going to take a moment to multiply it out. Just the x's, the major x's here. So I've got x squared multiplied by x is x cubed, and then I've got a negative here. So the dominant term is negative x cubed, which means it's going to start here. And if you want to, you can put the end as well, knowing that if it starts there, it's going to end in the diagonally opposite corner, or quadrant, sorry. Okay, that's all we need to do because we haven't worked out how to do turning points yet. Usually the instructions are pretty explicit, by the way. They'll say sketching all critical points, including turning points, or it'll say not including turning points, something like that. So you can look out for that. Okay, so there's my axes here. I'm just putting in the different points that I know about. So I've got y equals 2. So we'll make it here. Then we've got x equals negative 1. And x equals 2. Just trying to keep the proportions right. I probably could have used my space a bit better there, but that's okay. Now I know it's starting here and ending here. And it doesn't surprise me then when I have a look at the problem that the bounce is on, as in the repeating factor, which is where the bounce happens, is at negative 1. That kind of fits everything. So again, you can do a better job than I can in sketching. You can do it in parts if you kind of feel like that's easier for you. So you can sort of do a fairly steep curve there. And then you can't see me doing this, but I'm now moving my iPad around to do the rest of it. And sort of doing a sweep there, try not to make it as pointy as mine. And then it's gonna sort of, that was terrible, wasn't it? Do that, and then I'll get my rubber out and just went a bit too high. I don't really know whether that's how accurate that is. I'd have to use a graphing software in order to work it out, or use calculus to work out the turning point. But that's basically it. That's it, done. When I say I don't really know, I mean the turning point has to be between these 2 points, right? But where it is exactly, I'm not too sure. It's not exactly in the middle. That I can tell you. Example 4. It's probably worth just pausing the video for a second and asking yourself, well, what makes this different to the other examples? So pause the video and maybe think about it, look at it. What is it about this example that makes it different from the other ones? Okay, let's have a look at it. Hopefully you paused the video. Y-intercept, let x equal 0. What do we have? We have a -1 here, because that's gone. We have a 3 here because that's gone. So we've got minus 1 times 3, and we've got y is equal to negative 3. So 0, negative 3. X-intercept, let y equals 0. Let the null factor law take over. X minus 1 equals 0, therefore x equals 1. X squared plus 3 equals 0. Uh-oh. When we set x squared plus 3 equals 0, I'll just spell it out here so you can sort of see it. The value for x on this factor does not exist. So there is, in fact, only one x intercept, or 0. This does not produce any more zeros. So it's a bit weird. I wonder what that means it's going to look like. When you've done a few, you'll know what to expect it to look like, but until then, you can sort of just get the other key information and figure it out from there. Dominant term, x times x squared is x cubed. So what does that mean? It means that it's going to start here and end there. Okay, good. So draw my axes in. X and y, and put in my y-intercept, which is negative 3. So try and give it a bit of room. And my x-intercept, just the 1, is x equals 1. And that's basically it. Now, I know that it starts here and finishes there. So what it ends up doing is it just tends to wobble between the negative 3 and 1. We know that cubics tend to have a change in concavity. Yeah. So all we can really do is we can sort of say, well, there must be some sort of change in concavity here because it's sort of going through here and back through. So it's going to look something like this. There's a change in concavity somewhere in between these 2 points here, and that's about all I can say. It certainly doesn't do much more of a wobble than that. And that's basically it. So there's a fifth example I've got over here, example 5, y equals negative 4x cubed plus 19x minus 15. It isn't easily factorizable. If it were, you could just factorize it and just do the same as you did in example 2 from the previous video. But we're going to use example 5 to graph this using a GDC and working out the critical points from there, including the turning points, just for the sake of it. So I'll stop this video here, and the next video will be a skills lesson in using your GDC to graph a cubic.